So, in order to actually carry out bilinear interpolation practically, we need to do something that we already did when we looked at one-dimensional data. This time we define local coordinates u and v for our 2D grid data. U will depend on the x coordinates and v will depend on the y coordinates. But if you look at the form for u, then that is basically exactly the same as the local coordinate that we defined when we did one-dimensional piecewise interpolation. It's exactly the same, but now we have to append with it a second local coordinate v, which is very similarly defined, but defined this time based on the y coordinates. So as we discussed before already, the local variable u is basically an expression of how far we have moved along the x spacing, in this case, as a proportion of the whole width between two adjacent measurement locations in the x direction. So the red distance here represents x minus xi, so it's the distance from the starting point up to x, and the light pink or red distance here at the bottom represents the gap between successive locations in the x direction. And of course, y is actually very, very similarly defined. So in this case, dark blue over light blue represents the distance that we've moved up from yj towards yj plus 1, what proportion we've moved as a part of the whole gap between adjacent measurement locations. So these are just two local coordinates. So now we're in a position to write down our bilinear interpolation formula, and that is basically a blend of the four measurements at the four corners of the square that contains the point that we'd like to find the measurement for. That's represented by the pink dot here. So these four z values, these four measurements at the corners, are all blended by different weights, and these weights are determined by u and v. So zij, for example, has got a factor of 1 minus u, 1 minus v, whereas the directly opposite z value for this corner here is blended by uv, and these are the intermediate weights that are used for zi plus 1j, which is at the bottom right, and zij plus 1, which is at the top left. So these different weights can be sort of re-expressed in terms of the areas of the triangle, of the rectangles rather, the sub-rectangles inside our grid cell, inside our grid square. And we'll show that a little bit more clearly here. So here's our grid cell. The pink point represents the point at which we'd like to carry out our interpolation. And the four sub-rectangles are illustrated by different colors here. So this is green sub-rectangle here corresponds to the point that's marked in green here. This blue sub-rectangle here is corresponding to the point here, and this brown sub-rectangle here is corresponding to this point here, and finally the purple sub-rectangle corresponds to this point here. So each point has a corresponding subrectangle that is kind of opposite it in a sense. And the weights, so if we look at sort of the first weight, 1 minus u times 1 minus v, is actually an expression of the ratio of this subrectangle's area to the whole square. And if we move on to the next weight, u times 1 minus v is actually a measurement of this subrectangle's area as a part of the whole square's area. And correspondingly, we can continue. The purple area as a fraction of the whole can be written as 1 minus u times v, and finally the brown area as a fraction of the whole can just be written simply as uv. And that's because u represents a proportion along this direction and V represents a proportion along the y direction. So armed with our linear interpolation formula, we can start with our sampled measurements, and we can fill in all the little gaps in between by using our linear interpolation formula. So where we don't have measurements, these dark little gaps in between, we can fill them in using bilinear interpolation, and starting from our sampled measurements, we can end up with a picture that looks a little bit like this, which represents a kind of blurry or degraded version of our original signal. Bilinear interpolation can also be viewed as a convolution. So let's just recall what we looked at earlier, which was convolution in one dimension. Here it's illustrated by linear interpolation. So we start with our kernel h of x in this case. This is the linear interpolation kernel. And we have some data, some knot points, some control points, and some measured values. And this star notation is often used to represent convolution. And if we carry out our convolution, we'll end up with our shifted and scaled versions of our kernel, which then we can add up to provide our function here. So it's a summation written in terms of scaling with our y values, our copies of our kernel that have been shifted accordingly to our locations. Of course, this is all in one dimension, but we can readily extend this to 2 dimensions, except of course now we don't just have to shift and our kernel in the x direction, we also have to shift it in the y direction as well. So we can take our kernel and we can shift it so there's a copy in the x direction and a copy in the y direction, and we do a summation. This time it's a double summation because we have to sum over the vertical and the horizontal directions, and the scaling this time is by our measured value, which in this case is z, indexed by I and j, and we just do a product of the kernels across each dimension. Here I represents our x locations and j represents our y locations, and both of these indices range from 1 to m and 1 to n respectively. And what we get at the end of this is a function not just of x, but a function of x and y. We end up with a 2D function. If we have a closer look at this function, you might notice that the inner sum, part of it anyway, only depends on I. Here we have a term that depends on j, here we have a term that does depend on j, but just this part here, the shifted kernel that depends on xi only, actually only depends on I. So that means we can take this outside the summation and write it outside the inner summation but inside the outer summation, so we can put it here, and the convolution can therefore be slightly modified without adjusting it, without changing it, the actual formula. So we end up with an expression that looks a little bit like this. We have in the round brackets a set of terms that represent the z values multiplied by a shifted kernel, and then all of that is correspondingly multiplied by a shifted kernel here. So we can see what's inside the round brackets as being a 1D convolution, but this time it's a 1D convolution in the y direction, with j ranging from 1 to n. And the overall expression is actually also a 1D convolution, because this is just a shifted version of the kernel, but now it's being scaled by everything inside this round bracket here. So the whole thing of bilinear convolution can be represented as a 1D convolution over the results of separate 1D convolutions. We can visualize that separability of the convolution process with this diagram here. So let's assume that we have some data that's been measured on this grid here, and what we would like, we have our z values, each z value is associated with a grid point. What we would like to have is a measurement at some arbitrary location, here represented by the green circle. That's our target location that we would like to find a value for. And this is the convolution function written in its separable form. So the first part is to actually carry out convolutions in the y direction. So we treat each line of y data as a set of individual 1D measurements. And we carry out a convolution with the linear kernel along this line, and along this line, and along this column, I should say. And for each column in turn, we carry out a 1D convolution. And those separate red rectangles here are representing this part of our convolution function, because each one of these is carried out for a different value of I. Each value of I corresponds to one of these columns. Is that correct? Yes. So once we've done that, we end up with a set of values here shown by the red dots. Each one of those red dots represents a 1D convolution, a 1D interpolation over the columns. And the final step is to carry out a single 1D convolution over those intermediate results. So the red dots are now a set of one-dimensional data that we can apply our one-dimensional convolution to get our end result, to get our final value estimated at the target location. So now we'll turn to looking at data where the sampling might have been made at irregular locations. So we'll go back to the one-dimensional case to consider it because it's easier for now. Here we have an illustration of some measurement data that's been acquired at irregular spacings. So there's gaps that vary between successive data points. They might not be equal. Nearest neighbor interpolation is still easily applied. All we have to do is to put a horizontal function through each data point, and as we move towards the next data point, when we get to the halfway point between them, we have to jump to the next value. So we move along from each data point. When we get to the halfway point between it and the next data point, we have a discontinuous jump and we adopt the next value at that location. And linear interpolation is also still possible. If we recall, this was our local coordinate that we use to define over each interval, and it doesn't matter if the gaps between two successive data points, which is the bottom part of this fraction, are variable. It doesn't matter if they are different for different data points. We can still evaluate this local coordinate u, and so we can carry out linear interpolation fairly easily. In terms of the cubic interpolation, then Catmull-Rom will still work, whereas with variable spacings, de Boer interpolation no longer works. Now we can look at irregular data, but this time irregular data in higher dimensions. And a very good example that's very common in medical image analysis is surface mesh data, where we can represent a part of the body, an organ, here for example the brain, by a mesh, a surface mesh that is made up of basic polygons, and the simplest possible polygons that we can use are triangles. So our triangles are defined by sets of vertices, and each vertex can be associated with a measurement. And if we zoom in on this surface, we can see that it is in fact made up of many, many small triangles, and each one of those triangles is associated with a value. In this case, the value represents the curvature of the surface and is indicated by the color of the mesh. Now, if we want to carry out interpolation, we would need to drill down and look even more closely at this surface, and we want to focus in on a particular individual triangle. And that individual triangle, as we've said, is represented by three vertices, V1, V2, and V3. And what does interpolation mean in this case? Well, it basically means that there's some arbitrary location within the triangle that's away from the vertices in the continuous domain, and we would like to interpolate at that location whatever measurements we have at our vertex locations. And these vertex locations can be arbitrarily spaced, irregularly spaced within, in this case, 3 dimensions, and so it's different from the type of regular data that we had when we looked at images, for example. So one tool that we can use to help us to do this are something called barycentric coordinates. And basically, the idea behind barycentric coordinates is that we can express any location V that's within the triangle in terms of the actual positions of the vertices of the triangle. What we actually do in practice is to seek a set of weights, lambda 1, lambda 2, lambda 3. These are in fact the barycentric coordinates themselves. And what we require is that these weights can be used to blend our vertices. So remember, V here written in bold represents a vector, and it's in fact the position vector for V1, V2, and V3. Lambda 1, lambda 2, and lambda 3 are scalars, and these scalars are used to blend our vertices, and when we add them together, what we would like to have is that we end up with the position of V. And the main requirement is that the lambdas, lambda 1, lambda 2, and lambda 3, sum up to 1. So here's an example of a particular point inside the triangle, the point W. So in terms of its vertices, if we were going to write a blend of these vertices for V1, V2, and V3, then we would expect that the values for lambda 1 and lambda 3, which are used to blend V1 and V3, we'd expect those values to be very, very small. And because W is so close to V2, we expect the weight, the corresponding lambda, lambda 2, for this vertex here to be close to 1. So we can use these barycentric coordinates because we know that these lambdas, these weights, are used to blend the locations of the vertices to find any arbitrary point inside the triangle. We can use them also to blend the values of any measurement at each vertex. So let's assume that this color coding now represents a measurement value at each of our vertices. Then we can blend those values to get the value at a new location. So here let's assume that f represents a measurement of some function at each of our locations. Let's assume that our target point V has barycentric coordinates, which are expressed as lambda 1, lambda 2, lambda 3. Then these lambdas are used to blend the vertex locations to get the location of V, but we can also use them to estimate an interpolated value of f. So this time our three scalar values of lambda are being multiplied by the three scalar function values, or the three scalar function measurements, to give us an estimated interpolated value at the position of V. And here's an example where I've chosen a set of randomly chosen locations inside V, and for each one I've assigned it an interpolated value which is indicated by its color coding, and it's based on its barycentric coordinates, and it's based on the three measured values at each of the vertices. And for each point, once I've found its barycentric coordinates, its lambdas, lambda 1, lambda 2, lambda 3, I've blended the vertex function values together to get an interpolated value for all of these individual points inside. And we can see that the color values vary smoothly over the triangle. So far in our discussion, we've seen that we can use these barycentric coordinates to interpolate measurements at the vertices, but we've assumed that the barycentric coordinates have been given to us already. But actually, what we do have is just the point that's inside the triangle, and we need to find the barycentric coordinates for a given point. So one way to do it is to set up and solve a system of equations. So we have our three known vertices of our triangle here, vectors v1, v2, and v3. We have some position vector that we'd like to find the barycentric coordinates for. That's somewhere internal to our triangle. And we have our lambdas themselves. These are our unknowns. These are the scalars that we are seeking to find. So we can write out this system of equations. Instead of just writing it out as a single vector equation, we can separate out its components. So V1 has components x1, y1, z1. V2 has components x2, y2, z2. V3 has components x3, y3, z3. And V itself, our target point, has coordinates x, y, and z. All of these x's, y's, and z's are known, and what we're trying to find are our lambdas, the lambda 1, lambda 2, and lambda 3 that represent the barycentric coordinates for our point, our target point V. There is a constraint, however, on our lambdas. They do need to add up to 1, otherwise we won't end up with a point in the plane of V1, V2, and V3. So that means we can rewrite this constraint as lambda 1 being equal to 1 minus the other two lambdas, lambda 2 and lambda 3. So actually we don't really have 3 unknowns, we have only 2 unknowns. So we only need to solve, say, for lambda 2 and lambda 3 in our equations, and once we've solved for them, we can use this formula here, this simple formula, to calculate lambda 1 from the results for lambda 2 and lambda 3. So that means we only have 2 unknowns, so we only really need 2 equations, so we can drop one of our equations. And if we do that and do a little bit of rearrangement, then we can end up with a system that looks a little like this. So if you remember, this was lambda 1 in terms of the other 2 lambdas, and here's our lambda 2's, and here's our lambda 3's, and we've dropped the z equation and only retained the x and y equations from our original set. And we can take all of these and rearrange them one more time. So if we expand this bracket and collect together all the terms in lambda 2 and lambda 3, we can write it out in this form. xy is equal to x1, y1 plus some lambda 2's multiplied by a difference and some lambda 3's multiplied by some differences. This is just straightforward manipulation to get to this stage. Once at this stage, we can rewrite it a little bit more easily by taking some of the values over to the other side and providing us with a simple matrix equation. So this time it's a simple 2 by 2 matrix multiplied by some lambdas to equal a difference between our target point locations and the first vertex locations. If we just go back to the original from the previous slide, you can just see what we've done is to move these terms over to the other side and to rewrite this part here as a matrix multiplication, and that's written here. So we can solve here for lambda 2 and lambda 3 very easily by just inverting a 2 by 2 matrix. And we take that inverse and pre-multiply it by this vector on the right, we'll get our lambda 2 and our lambda 3. Everything that we've done in the last few slides has taken a very algebraic view of these barycentric coordinates and has manipulated their equations in purely algebraic terms. And the next few slides we're going to take a slightly more geometric view to see what's actually going on underneath the geometry. So let's look at the geometry of the barycentric coordinates that we've looked at so far. So we have 3 vertices with some measurements associated with them. We have a target location here shown in red, and we can take our triangle that is defined by our vertices and we can use 2 edges of this triangle to define 2 vectors. These 2 vectors are shown here in blue and in red, and they're very readily calculated from the vertex vectors that we have. So this is v2 minus v1 and this is v3 minus v1. These 2 vectors, we can look at them as a kind of basis, a local basis, that will help us to navigate around our triangle. Any point in the triangle, we can reach it by going from the origin up to v1 and then adding a fraction of the blue vector and a fraction of the long red vector. Lambda 2 times the vector that goes to v2 and lambda 3 times the vector that goes to v3, with lambda 3 and lambda 2 being fractions that are smaller than 1. These are all illustrated here. So if we want to get to v, we first go to v1, and then we add on a fraction of the vector that takes us to v2, and then we take a left turn and multiply by a fraction of the vector that takes us to v3. We can go either way. We can go this way and up, or we can go that way and across. So this is now our vector formula for reaching v. v1 plus lambda 2 times the difference plus lambda 3 times another vector difference. If we compare this with our earlier equation that was derived from the components, I hope that you can see how basically it represents the same information. So location is equal to the location x1 plus lambda 2 times the difference plus lambda 3 times another difference. So if we collect our terms together here, if we multiply lambda 2 times this bracket and lambda 3 times this bracket, then we can bring out everything that's in terms of v1 and v2 and v3 and separate them out. And so we end up with this expression here. And given that we know, well, we can define even lambda 1 to be equal to this, what we do is we basically recover our definition of what the barycentric coordinates are. Remember, our definition is that one position inside the triangle can be written as a blend of the three positions around the vertices of the triangle. And the blend is weighted by our barycentric coordinates themselves, lambda 1, lambda 2, and lambda 3. So as a summary then for barycentric coordinates, we now have the tools to calculate the barycentric coordinates for any given point inside the triangle. That's our lambdas. And we can do it using a simple 2x2 matrix inversion and a little bit of manipulation. Once we've found them, then we can interpolate measured values that are given for the vertices of a triangle. So if the three different vertex locations, v1, v2, and v3, have measurements f1, f2, and f3, then we can use our barycentric coordinates to blend our measurements to provide an interpolated value at our target location v. And we have to recall that we did all of this to interpolate some irregular data in this case, in 3 dimensions, or it could even be in more dimensions. So as a summary for all the notes in the lecture so far, I hope that we've learned about regular data, lattices in 2 dimensions and higher dimensions. We've also looked at irregular data in 1 dimension or on meshes. We've discussed approximation, either polynomial approximation or kernel approximation, and the errors that can happen with that. We've looked at convolution for interpolation. We've done it also in more than 1 dimension. And we've also looked at convolution as a way of viewing the process of approximating data. And we briefly looked at also extrapolation, where we actually find explicit functions based on our measurements to give us out-of-sample estimates. And bilinear and trilinear interpolation are popular methods for higher dimensions.